All right. So welcome everyone to a new edition of this colloquia of the research division of the IAC. Today it's my pleasure to introduce and welcome Anatael Cabrera. So who is Anatael? Anatael is a world-renowned expert in neutrino physics, in particular in experimental particle physics applied to neutrino physics. He has been in this field for I don't know how long, 20 years, more. He's been designing and leading experiments to try to detect neutrino fundamental properties in oscillations of neutrinos coming from nuclear reactors, but also from the sun. And he has also been leading some new design of new technologies. No, I guess we will also talk about this a little bit. So as such, I mean, he's very well known. He's leading now experiments both in France and in China, Double Shoes and Juno in China. And as such, he has had many representation roles of these experiments, spokesperson of Shoes, I think. And also he's very well aware and an expert on analysis, not only in design and technology. As an anecdote, I would also like to mention that Anatael Cabrera is a far relative of the famous Blas Cabrera and Felipe, who was the pioneer of fundamental and physics in Spain in the early 20th century. So he has been basically filling the shoes of his grandfather or uncle, father, something like that. Okay, so thanks for accepting our invitation, Anatael, and the floor is yours.
Thank you very much. It is a big pleasure to be here. In a way, in an international collaboration that I am, but actually coming back home in a way because I'm originally from the Canary Islands myself, so I'm most of the time in Paris. So the challenge of today's talk is to tell you a little bit about neutrinos without saturating you, and maybe how that relates to the IAC or IAC. And there you go. Okay, so first thing, I mean, to kick off, I mean, let me start by my conclusions, as a matter of fact. Neutrinos are probably something you know everywhere. As you know, neutrinos are one of the most abundant particles in the universe. And so it's going to be actually rather easy to find relations between the IAC, in fact, work, and, oh, thank you, and neutrinos. Neutrinos are also produced virtually also everywhere. As a matter of fact, it's actually hard to find places where neutrinos are not produced. And the main reason is that if you have any fusion or fission or just radioactivity or any decay, like basically neutrinos are going to be there in one way or another. Neutrinos are providing complementary information. Oops, is that what you wanted or not? Is going to provide complementary information. And this is particularly important in today's vision of the universe from different angles. This is the multi-wavelength observations. Neutrinos, as we're going to discuss, essentially, they shape the universe. I mean, we're going to see that essentially neutrinos play a role in many ways. And one of the key things is that they have some mass, minimal amount of mass, and minimal ability to interact. And this is going to give them a very peculiar property in the universe. And is this free stream and this ability to carry out information. And this is going to be fundamental to catalyze, essentially, even, for example, supernovas. And so this key feature is going to be basically present all the way. And something that often people don't actually realize, maybe this is because this is a later vision of neutrinos. Neutrinos may be linked to our own existence. We are made of protons and neutrons. We're not made of neutrinos for evident reasons. I mean, and nonetheless, we think that from the Big Bang, if we try to understand the Big Bang today, actually neutrinos may play a critical role there. So that sounds beautiful. And there's going to be some paths, I mean, that I'm going to highlight basically as I go along. let me basically emphasize when it comes to neutrinos, we are often talking about in the high energy physics, particle physics basically world, and there are basically 4 huge laboratories. There are many others, of course, but 4 big laboratories, of course. CERN's very heavily dedicated to LHC, but these Fermilab, basically in the United States, IHEP in China, and KEK-JPARC, they are very heavily dedicated to neutrinos, as a matter of fact. So one of the key things basically in particle physics is that neutrinos are becoming more and more essentially a leading role. And the main reason is because we have been going through a lot of basically good news with neutrinos. I'm going to basically try to highlight that as we go along. Essentially, many discoveries has been catalyzed basically every single time we try to understand neutrinos in one way or another. Essentially, we realize basically there is something really interesting actually going on. There are many open questions to understand the standard model of particle physics, like understand that our universe in many ways. And unfortunately, it's not as straightforward to know exactly where to basically ask the best questions. And neutrinos may be one place to go. And I'm going to try to basically convey all that to you in this morning. To highlight basically the interest of what is happening basically worldwide, this laboratory Fermilab, so this is basically the CERN equivalent basically in the United States, it's the biggest laboratory in particle physics, now basically calls themselves the capital of the neutrino. This was basically a collider, basically laboratory, and today is becoming twisting entirely the program and is going to become one of the most important laboratories when it comes to neutrino physics, and I would highlight that. Neutrino physics basically also has an endeavor of making a spectacular instrument. So this is the supernovae basically detector in Japan, and these are some particle physicists repairing essentially some photomultipliers. These photomultipliers are roughly speaking of the size. And this is ultra pure water, and this detector is 50 meters by 50 meters. This is 50 kilotons basically detector, and that's the kind of detectors that we need to do neutrinos. Beyond, the problem with these detectors, there are going to be some issues appearing, because detection indeed is going to be the biggest problem. So it couldn't be always good news. The bad news essentially is the neutrino detection remains basically very complex. And this is to a large extent something that cannot be basically helped in a way. And the main reason is because the cross-section of the neutrino, the probability for the neutrinos to interact is actually extremely low. And that is its advantage and disadvantage at the same time. But of course, that makes detection extremely hard. Detectors need to be large or even huge, and they have to have a huge sensitivity because neutrino interactions is basically one. You would see even radioactivity in the detector basically is an issue. This is why these guys are dressed in very clean cloth, because even your own, basically even the hair of your body basically is radioactive, and this is something you want to avoid in this kind of detector. So you need to make something huge, and at the same time to control every single thing that goes inside. And simplicity is very important because you need to make something huge. You want to keep the cost basically low. And this means you have to make something very simple. And you would see that that is going to be part of the problem. Is low cost simplicity and making something huge that has a lot of basic information is the compromise. It's the art of detecting neutrinos. And that's going to be tough. But nonetheless, you see some interesting basically elements there. So in fact, this constraint that is almost basically pushing one against the other is going to make detection technology actually complicated. And this is going to basically be, the big issue is going to be controlling your backgrounds, things that mimic the neutrino signal in your detector. Let's go through that. So this is basically the hyperchemical construction. This detector is now going to become 10 times bigger to what you just saw in the previous slide. So this is actually being built right now. So this is basically order billion euros basically investment that is happening right now. This is actually United States. There is a big project called TUNE, actually from Fermilab, basically with accelerated neutrinos, shooting basically over 1,200 kilometers, detect neutrinos on the ground, essentially, no pipe. The neutrinos just go through the planet, and they are building this huge facility basically in Dakota. And this is deep on the ground. This facility where the detectors are located, this is 2 kilometers roughly speaking, underground. So this is another complication for neutrinos. We need to build all this stuff deep underground in order to protect the neutrino, the detectors, because they are so sensitive that just the cosmic rays actually is a big issue for us. We actually require basically huge infrastructure. So this is an experiment that I'm working basically on in Juneau. This is close to Hong Kong. This experiment has just starting to take data as we speak. And this was basically a few months ago when we were building this detector. And this is going to be using reactor neutrinos, as a matter of fact. There are other kind of even funkier type of neutrino detectors. There are neutrino detectors basically hidden under the Antarctica. So this is what we call a neutrino telescope. And this is a huge basically detector that is 1,000 kilometers basically tall. And this is basically a huge detector, megaton basically kind of capabilities. And this is because we want to see the stars. And if you want to see basically the stars, you will see that later. Essentially, you need to make even bigger because the probability is not just the cross-section now, is basically that these are rare events, as a matter of fact. But we actually have these kind of detectors, these astroneutrino detectors or neutrino telescopes. We have them basically under the Antarctica, under the ice, but we have them under the Mediterranean. And even in Baikal, basically lake in Russia, we also have basically a neutrino detector basically doing this kind of physics. So as you can see, we're pushing hard basically the boundaries basically of what mankind can do, humankind can do essentially to neutrino physics. So how is all that related to the IAC? So this is the challenge basically of my talk. This is going to be just an appetizer. Essentially, I cannot really go through everything that we're doing in terms of neutrinos. And that's a little bit of a challenge. And I apologize in advance if I've missed out essentially your favorite neutrino experiment there. Before I really go into what we're doing, let me remind you what neutrinos, what do we know about neutrinos? So when it comes to basically particle physics, we believe basically, or at least the evidence basically right now is that we have three fundamental particles. And out there, with some leptons basically and quarks, neutrinos are actually the leptons basically side. We have at the very least basically, we can call it three fundamental interactions, which are quantized, electromagnetism, nuclear weak interaction with strong interaction, essentially. And these are, in today's vision, they are mediated by bosons. It's just to put in context, I'm going to basically skip later on. Gravitation, not quantized, or at least no evidence essentially for the manifestation of quantization, as Jorge actually explained to me recently. I mean, we can think of it, I mean, from a geometrical point of view, but also from a quantized. And why do we basically see that? Well, nobody have a clue. The reality is that the standard model is just a description of what we have seen, and trying to understand the relation between these lepton and quarks and all these relations is actually all physics beyond the standard model. We do not know where we have leptons, we do not know where we have quarks, we do not know the relation even between them, we do not know whether they are related or not related, and this, as a matter of fact, is something that basically we want to understand via the neutrinos, and I would emphasize. Okay, neutrinos, there are three types of neutrinos linked to the charged leptons, so called charged leptons, electron-neutrinos with tau, and there's been basically the discovery of these two neutrinos actually were heavily celebrated essentially in the community. The tau neutrinos were kind of expected regarding why normal price was being that. Well, say that again. I mean, this was kind of expected because we were in the world three boundaries. Storage rules, of course. Why neutrinos only interact with interaction? Well, we don't have to, as a matter of fact, you know, one of the mysteries, but that is basically its key feature, and that's going to have a lot of implications. Because of the same thing, we don't know whether neutrinos and antineutrinos are the same particle or not, as a matter of fact. And that is actually something very profound, because it may have implications even to our own existence. If neutrinos were their own antiparticles, as we don't know, we would call neutrinos Majorana particles as opposed to Fermi, Dirac particles. And this implies essentially that these neutrinos may have been generated in the Big Bang, and these primordial neutrinos may be at the heart of our existence. And this is something that we don't know yet, but we need to understand it. And if anybody figures that out, then possibly that's going to be heavily celebrated in the long run. Neutrinos are called neutrinos because of the neutrality in terms of electromagnetism, and this is why the name basically was chosen. Of course, it's different from a neutron. Why are they neutral? Well, actually, there's a mystery, because if you think about it, neutrinos is the only massive particle that doesn't have a charge. Everything else that has mass has no charge. That, again, we don't know why that is the case. Keep in mind that neutrons are not fundamental particles. It's a composite particle, they occurs. So therefore, it cannot be compared to the neutrino from that point of view. So there are several questions that we don't understand from that point of view. Neutrinos, because of this not charge, cannot make matter, cannot make structure, cannot make any composite that can happen like. And this implies neutrinos are going to behave like normal particles in the universe. It's going to behave like a wind carrying information, and with this, all the property that they value is right. So neutrinos are going to work in this way, and this is going to be fundamental even for our own existence, because if there were, for example, no supernova, we wouldn't be here, and neutrinos are key essentially for that. Neutrinos do have mass, but it's a small mass, and this is why Fanny essentially at the very beginning is called the neutrino, separate from the neutron. And now we know that neutrinos propagate in a very funky way. This is what we call neutrino selections, and this implies the neutrinos mix. So actually, we actually see a composite of system, and these are mixed, essentially the neutrinos are mixed, and this is because of neutrino massive eigenstates and the weak eigenstates, they mix in a non-trivial manner. Long story short, I'm going to give you the theoretical details, but if you have any question later on. But the oscillation manifestation is also to do with mind, and we don't understand why that is the case. Fundamental reason why it's happening, we do characterize how that happens. We understand this now very well, but we don't know what is the fundamental basically reasons why that is happening. Nonetheless, it's interesting because that happens something very similar happens with works, no matter that. Neutrino feature number one is elusiveness. Long story short, neutrinos can go through huge amount of matter, where, for example, going through the planet is just a prominent part. Neutrinos go through the planet, we detect them nonetheless, and of course that's going to make basically the problem of detection very important. And neutrinos actually coming from there, we can see them too. So this is a very nice way to actually look basically at the core of the planet, and I thought about we're doing that. And of course, basically, this feature is going to play out very bad when it comes to detecting them. And that's actually my job, in a way, with many of my colleagues, of course. And this remains probably one of the most spectacular basically achievements in terms of scientific essentially detection. We're looking for things like that. Now, neutrinos, as highlighted, were needed in core collapse supernovas, like for example in 1987, and they were detected by the Cabrera detector. In fact, this was a Nobel Prize, and this is because neutrinos, 99% of the energy basically released essentially in a supernova are actually coming from neutrinos, and thanks to the neutrinos, in fact, the supernova actually collapse, and this is basically why we see in many ways, because this is the fabric, well, not the fabric, actually the factory of heavy elements that they happen typically in supernovas, and this is the only way to get stuff about basically ions, otherwise we don't get them essentially in the future. And this happens very quickly, and you get this bar of neutrinos over a few seconds time scale, and many detectors are basically are ready to catch that. The disadvantage is that supernovas of this type happen with an average of 30 years. That means that we are just about to have another one very soon. Of course, wasn't statistics driving the equation, and nonetheless, basically this happens. And again, this free streaming, this ability of neutrinos to move energy essentially away from a certain place with no interaction, is actually fundamental for essentially for supernova with vectors. Neutrinos actually were proposed well before actually they were detected. You know about Pauli basically, and I'd like to highlight basically that Pauli, when people were trying to understand this, the beta decay, this was just the basic decay, long story short, essentially people were absolute desperation. I think important to highlight because the context of this we have to data. People were not understanding why radioactive basically decay. They were having two particles that people could measure, one of them being a beta minus essentially. And people were ready, basically, were seeing that there was something was not right. It was looking like conservation basically of energy was not happening there. Of course, these, as you know, basically a failure when it comes to basically a lot of physics. Bohr included was basically ready to abandon basically the principle of conservation of energy. And this implies how desperate we were. And Pauli came along and he actually suggested, actually, guys, hang on. Actually, we see two particles that even there may well be another particle that we can detect, but energy actually is concerned. And think about it, that's kind of cheap. Well, I'm solving a problem that created another problem that is not valid as a matter of fact. And in fact, Pauli knew that. Pauli said, I'm very sorry to propose something that is like basically just solving a problem, but like creating another problem that is even worse to some extent, because the question was, can we detect those neutrinos ever? And the answer is, of course, yes. And that will happen basically 25 years of freaking later. And we need technology for that. But it's very important to contextualize that. Why this is important? Because in fact, existence of neutrinos changed the entire way of thinking. You would see that. It was a revolution, as a matter of fact. We started realizing it can be stuff that we cannot see, that can be catalyzing what we see. And that actually is a pillar of modern basically physics. You will see biophysicists, every time there is a new phenomenology, new something that we don't understand, people say, oh, just a new particle, exactly basically happen. At the same time, you may laugh, because sometimes it's actually laughable. Sometimes that is fundamental basically profound. I'm not sure basically when that's right or wrong, I'm not going to judge, but you will see papers and papers and papers and papers coming with the new particles, or maybe that you will have it, long story short. But that clearly has changed entirely our way of thinking of the cosmos. There are things out there that may never even manifest. You may hear about sterile neutrinos. You may hear a lot of things that basically are out there, and the reality is that for as long as physicists, for as long as we can prove otherwise, that possibility is there, and we just don't care. Right. So in fact, right now, we think even the universe is made of a lot of things that we cannot detect or we don't know it. Dark matter, that energy, which are fundamental particles potentially for keeping basically civilization in the force, in the strong force. These are basically something that people are searching with a lot of basically emphasis because this particle is actually heavily motivated. But this is not the first time that something very heavily motivated with theory turns out not to be there. It turns out to be completely different. So this is a fascinating problem nonetheless, no question about it. Understanding the standard model, and we highlight basically this success. If you look at basically particle physics, and you look at the result of IAC, for example, you can see that the standard model and the experimental basic results are scary, beautiful ability. We say, wow, that's success, indeed, that's a success, but we don't understand why that happened because we know actually that the standard model is complete. We know that we couldn't understand our existence essentially with the standard model as it is. We know we need CV validation, for example, in the Big Bang to be here, and we know in the standard model there is not enough CV validation essentially for us to be here. So in fact, we should really, in a way, I mean, the biggest mystery of the standard model is how could it be so accurate on so many things? Nonetheless, we know this is complete. And the big question is, what do we search for? Where do we go? Where is the right place to go? And neutrinos seem to be, seem to be one of those places. I'm going to highlight this in the following slides. But of course, it's not the only place. Actually, looking at the sky is one of the most fundamental ways to look for the new star. Of course, the only way to solve this problem is better experiments, better observations with higher sensitivity, because it's not a theoretical problem. It's an experimental problem. We need to understand, we need to see new phenomenology to be able to help the theories essentially to figure out what actually is happening, what is actually missing in the standard. And that, in fact, is what we're doing in particle physics, but everywhere. It's not a biased field. So neutrinos are everywhere. They are in the Big Bang at low energies, and this is part of basically a typical discussion that cosmologists basically have. Neutrinos are in the stars and the supernova. They are in the birth and the life of the neutrino of the stars. And this is basically something that is typically basically observational astrophysics basically know. We can basically look at our sun being our closest basically star. They are basically in the solar model, basically in the solar system, sorry, in the formation and understanding of that. I will highlight later on planetary astrophysics, but understanding the Earth in itself isn't far from a complete problem. I think basically I will emphasize in a few minutes' time. And trying to understand neutrinos at high energies is also trying to understand basically completing the battle of the cosmic ray and gamma ray astronomy, long story short. And so the neutrinos are fundamental for that, and I will emphasize that later on. And trying to understand the most fundamental basically elements of our science, basically the standard model of Young, theoretically, astrophysically, or just like physics, essentially, this is also where neutrinos are going to play a big role, including over our existence, I highlighted before. The challenge, basically, again, is going to be to detect them. Actually, neutrinos are happening everywhere. You're being hit by neutrinos, you're actually neutrinos, as a matter of fact. Big issues about the significance of your ability to develop what hit by a neutrino, which is activity, and it's about background. Basically, that's the name of the game with light and so on. Neutrinos are actually reached many milestones, and I'm going to highlight its highlights, and I'm going to highlight later on the problems. Neutrinos basically were discovered with reactive neutrinos in the 50s, in fact, but today they are limited by backgrounds, and it's a technology problem. They were actually also detected in the solar neutrinos were detected in the 60s, and they are dominated by vacuums today, technological problem. They were atmospheric neutrinos were detected in the 80s, and they are also dominated by vacuums today. Supernova collapse basically in 1987 was also measured basically in the 80s, well, in the 80s, probably not right until the 2000 on the left, and this is also dominated by vacuums, no problem. Now we're using accelerators to generate neutrinos, essentially, and this is actually right now limited by the accelerator itself, but very soon we're building even more out of this new experiment in Hyper-K, we're using accelerators for that. Very soon systematics are going to be there, and technology of vacuums are going to be the big issue. Geoneutrinos, neutrinos from the Earth, were discovered in 2004. They are dominated by the vacuums. Great neutrinos, the neutrinos are well generated essentially with the Big Bang. Essentially, I mean, these are actually something we haven't seen, but if anybody sees that, that is going to be highly appreciated by the community. And there are two very related topics to neutrino physics, to usually neutrino physics, is understanding whether there is a double beta neutrino-based decay, because that would imply neutrinos are its own antiparticle or not. And this is one of the few ways that we prove that. If anybody solved that problem, or anybody sees proton decay, proton is basically neutrons decay, but proton do not decay. If anybody sees proton being decayed, this implies that we are seeing decay of the universe, which means that for the lifetime is into the universe. So understanding proton decay is also fundamental thing. And a lot of these neutrino experiments were not born just doing neutrinos. They were born searching for proton decay, because that implies new physics. It implies that protons became something lighter, and that in the standard model is forbidden. So if anybody solved any of the three problems, I mean, be sure we're going to be highly appreciated. Many histories associated with the standard model. Again, we don't understand a lot of that, and a lot of that is limited by technology. So I'll come back to this as an experimentalist and biased from that. I'll emphasize technology later on. These are basically what these neutrinos, if you look at energy over many orders of magnitude and many orders of magnitude in flux, these are basically where the cosmological neutrinos are down here, and this is because they are redshifted essentially from the beginnings. I mean, they are very low energies right now. And that's the problem. Typically, the detectability starts by the key kind of level. When you go to those energies, you really need to apply techniques that are not common part of physics. People are trying to do that. That's not. To say the very least. As a matter of fact, nobody has achieved that. The discovery of the neutrinos were done with artificial neutrinos, ironically, but everything else is natural sources, as a matter of fact. Solar neutrinos are here, supernova neutrinos are there. Basically, geological neutrinos or geoneutrinos are basically down here in the region. This is radioactivity, natural radioactivity region, essentially. And then there is high energy neutrinos, essentially, in that region. And this is where we're really today to the galaxy, essentially, because we're very involved beyond the galaxy and the galaxy of the galaxy. So there is a selection of neutrinos missing here, very roughly speaking, in the GeV range, roughly speaking. So as I started at the very beginning, the neutrinos are just everywhere. Long story short, the big issue is that there are much more neutrinos, but we cannot detect them. The lower the energy, the harder it becomes. The higher the energy, that is actually very easy to see the neutrinos. The problem is that they are very rare by several orders of magnitude. So that's really unfortunately the challenge that nature has given to us, and there is nothing I mean to rant about. We just have to tackle and do our job. So let me talk about detecting neutrinos, and again, technology is going to come about because everything, I mean, the question and the battle about improving the technology for neutrino detection is open, well open. Everything actually started basically by Oppenheimer's basically team. As a matter of fact, it's something that many people don't know. It's kind of surprising. This is Oppenheimer. But if you actually look at basically this small section of his team, so this is the actual basically pictures of the team, you will recognize Fermi basically. This is Beta, this is Alvarez and Feynman, actually Feynman basically. So you will recognize very famous people there. But there is another very famous guy, Brainless. He was in the team, and he was not surprised by actually discovering the neutrino. The very beginnings, you may remember, is actually proposal for detecting neutrinos. It was something very simple. You actually make a bomb, an atomic bomb basically explode, basically up here, and you put a neutrino detector that you're going to let it fall, and basically fall into something soft. And during basically the free fall of that detector, there's going to be neutrino detection. Okay, this is just a byproduct of basically the bomb, basically the Manhattan basically project. The reason why people were thinking about it is because everybody was there, as a matter of fact. And then, of course, they realized that there are certain disadvantage, to say the least, when it comes to basically doing some nuclear tests, and this is basically Los Alamos, nearby Los Alamos basically at the time. And people realized that actually maybe we just go to a nuclear reactor and we're going to be better off. This is very stable, less explosive, and this is actually very nice to go. Ironically, this anaerobic reactor where the discovery actually took place was actually where plutonium was being generated from the bomb, as a matter of fact. So actually, this was one of the several reactors that actually was basically run at the time, essentially for discovering the neutrino, but most importantly, that was part of the program basically we had. Long story short. So this was 1957, and since then we have been basically progressing as highlighted basically before. Now, let me just make some highlights of what I cannot cover everything, but let me basically highlight a few things related to the regulating neutrinos. So basically that was happening in 2004. In 2020, CP validation is starting to manifest in neutrinos. To be very honest, actually, I was the reviewer of that paper. I didn't expect the newspaper to go on the front of Nature. We are getting to sigma, so we're far away from 5 sigma basically to claim that the CP validation is there. So I have to say, I mean, I think it's a bit of a big claim here. But nonetheless, I mean, it's a very important topic. CNO solar neutrinos were seen only recently in 2020, and this is something that we know. CNO, of course, is one of the driving processes for normal stars, the big stars generally. And very recently, just a month ago, the first PeV or PeV neutrino basically was detected and also highlighted very recently. So I'm going to go through some of that. But before that, let me highlight a little bit of the news in terms of neutrinos at low level. So this is basically sort of solar neutrinos and so on. So this field, that these energies, people has been totally dominated by this neutrino oscillation basically phenomenon. And the reason is very simple. If we don't understand how neutrinos propagate, so these neutrinos is what happens to the propagation of the neutrinos before, after the production and before the detection, essentially we don't know how to interpret neutrinos, long story short. Now we know neutrinos are massive, thanks to that. And we know basically this is basically introducing the standard model, and massive neutrinos have different phenomenology because they play a different role. Again, neutrinos were massless. They actually basically carry energy in a different way. Basically, neutrinos are massive. If neutrinos are massive, actually, they play a different role in cosmology and supernovas. In fact, that is free sweeping approach to the physics that I highlighted. So neutrinos being massive is fundamental, essentially, to understand the role of neutrinos in the formation of the universe, long story short. Interestingly, by actually doing this phenomenon that was unexpected, neutrinos and quarks, leptons and quarks, they look a little more similar. We had mixing and CP validation for Nobel Prize in the 60s, basically from Anatael. Basically, they discovered those CP validation works, but we didn't know there was any CP validation whatsoever, potentially leptons. And these basically physics basically puts CP validation into the lepton sector. And it is very interesting because again, as I added, we need CP validation to exist. We know that quarks CP validation is just about 3 orders of magnitude short to justify our existence. So this means maybe neutrinos are the answer to understand why we exist from the Big Bang. And this is why people are very excited about CP validation in neutrinos, even though these light neutrinos CP validation may not be the CP validation that we wanted in the Big Bang. Nonetheless, this is progress and moving in the right direction. This field at MEP, we were driven by relativity. Relativity was a pain. Our own presence is a pain for our detectors, long story short, and we have been developing over many decades, and I'm going to go into details, techniques of purity, and that's been a breakthrough. I would say that speaking productivity, our own productivity, we know how to handle it in our detectors. Cosmogenics, though, things that basically come with cosmic brains, essentially, this is a big issue. It remains a big issue. And these answers, many of the pictures I showed before, this is why we have to put the detectors underground, or under sea, or under ice, or under whatever the hell we can, because there is no way to solve basically this cosmogenic problem. Actually, I'm going to come back to that, and maybe we have some solutions there, but these remain officially not an unsolved problem, and this is why we need to push the neutrino detector into the long story short. In this NEB, I mean, we are understanding even to the per mil, getting to the per mil level in terms of neutrino oscillations. So this means that now we really understand how neutrinos propagate, provided that's the end of the story, and there is not another ripple, if you like, on the fundamental physics of the propagation of the neutrinos, and that actually is being searched for. So we're trying to understand, is this the end of it? That was easy to integrate in what we call the Southern model, but there is room for other manifestations that we're looking into that. So what's next? Well, as you know, typically yesterday signal is today's background. We are looking for the new possible manifestations of new physics, and that's a lot what we're basically up to, essentially, and I will highlight this in the current example. Regarding the NAV, though, let me highlight something interesting, because trying to understand our planet is far from settled. You'd be surprised, I mean, I've actually been working a little bit on that, I mean, with some geologists, as a matter of fact, and I was very surprised to realize that actually our understanding the modeling of the planet is actually far from complete. We don't understand very well the magnetic field and all this, and the energy, how the energy, the heat basically of the planet that is actually producing the LNCA, the motion, and so on, the history of the planet, long story short. And a lot of that basically could be resolved, crazy enough, by actually looking at neutrinos from the radioactivity of the planet, the uranium and the thorium and potassium, essentially of the planet, and that basically was discovered in 2004. So we can go farther on that, and that's interesting because that is actually what people try to understand using seismology, but also asteroids, like probing basically the solar system using asteroids and trying to see the composition, both because of they were made of the same basic materials, that's assumption. But using neutrinos is a complementary way to actually try to basically get into the planet, actually the tomography of the energy mechanisms of the planet. And this is something that is actually being done. So the first observation was in 2004, and we are seeing these uranium and thorium neutrinos at very low energies. This is radioactivity level, because this is coming neutrinos from the radioactivity, as a matter of fact, from the uranium and thorium basically chains. The reality is we're seeing very little, because if you look at low energies, there is a lot of geoneutrinos down there, but we have an interaction that basically its threshold is here, and nobody has been able basically to lower the threshold down here, and there was no interaction now, as a matter of fact. And there is another contribution which is huge, which is potassium-40, is a much larger material that people don't understand where the potassium-40 of the Earth is. You know where at the very beginning of the planet, the potassium-40 evaporated, it's like that. Or when the potassium-40 actually became the planet, and it's actually down there somewhere, but iron-40, the gas, as you know, comes from potassium-40, okay? And we know that the iron-40 comes only from potassium, mainly from potassium-40. So we're trying to understand what happened to this potassium-40 that not only explains this iron-40 that we see in the air, but also to try to understand basically the energy and the mechanism basically of the planet. And in fact, only recently, actually, with some collaborators, we actually proposed a new interaction. Seems the only interaction that we may have in the universe. We looked at all the nuclear databases, and this appears to be the only element that might basically provide the solution to see these potassium neutrinos, but we would have to work very hard for that. If you're interested in the details, this is the paper, roughly speaking, and the strategies to see the fact that neutrinos from the Earth are not actually neutrinos, they are anti-neutrinos. But the Earth is emitting antimatter when it comes to neutrinos. And this is because the decay of matter generates antimatter in terms of neutrinos. And that's very nice because antimatter neutrinos manifest like positrons, and positrons is actually a very rare basic occurrence in the Earth. With the same technology, this is just a little bit for amusing because actually I'm in a meeting with the IAC like at night. Essentially, we're trying to use the same technology to provide tools, essentially, to situations like Chernobyl or even Fukushima, because understanding, measuring the neutrinos of the planet is measuring the neutrinos or antineutrinos in a nuclear reactor or nuclear fuel, basically through uranium and thorium. So these technologies were looking very heavily to try to help out essentially our friends in the nuclear industry, but also basically the United Nations. Long story short. Now, let me go to GV and give you a little bit of an appetite of what's going on. Well, since the 80s, we have been focusing again, essentially in the neutrino oscillations. It was the Nobel Prize in 2015, as you may know. And the next step is understanding the CP validation that I highlighted before. The first evidence was highlighted in this paper. Evidence mainly to hard wall is a 2 sigma effect. And nonetheless, this is remarkable as I highlighted because we are hunting for city validation forces in the universe, and we don't have enough in the corpus sector. Productivity is not an issue for photogenics. It is an issue. It's very surprising. The GEV, our detectors, cannot handle that. And this is because we're bombarded with elements like these red cosmic rays, and we just have piled up, and we have a lot of rubbish in the detector that we take data. Typically now we're using accelerators. Accelerators are clock machines, so we know exactly when basically the beam comes, and basically we can detect better. That's very nice. But I mean, beyond this GV going higher, basically to the PV, TeV above, essentially, we're looking for, after basically neutrinos, and this is complementary, of course, basically to the field in terms of cosmic rays, gamma rays, and everything that's part of that. And probably one of the key things understanding smoking basically sources for the first time. So I would highlight basically a couple of elements regarding that. So I think I don't have to explain basically here very much basically that the advantage of the neutrino again is inability to interact would allow us basically neutrinos to point directly basically to sources, of course with some uncertainties coming from the detector, as opposed to cosmic basically rays that they are charged particles and magnetic fields, even they're small, basically they can cause basically some scattering because of the long distances. Gamma rays are better from that point of view, but they could be also basically approaches and scattering. And so that basically this is why neutrinos are, of course, the way to look at it is to look at everything, long story short. The neutrinos not only can tell you about what happens on the surface of anything, but can tell you what happens even inside, and that's the other nice feature of the neutrinos, of course, looking at black hole. But nonetheless, neutrinos can tell you about something that happens inside, and we'll come to this point later on. And this is actually very nice to look at in all possible ways to see the validity of our models, understanding basically these very high sources. Big problem, of course, is that the flux is going to be low. Generally in this, because we need to be very lucky for the flux to be relatively high because the electron probability remains very low. So it's very challenging to see neutrinos in astrophysics because, of course, the solid angle is very low. Of course, we can basically look into it in a combined manner, and of course, basically here in IAC, we have basically magic and CTA basically being the long story short. So the first PV neutrino was detected actually in 2023, but it was released only 1 month ago. Several basically papers basically came out. And it's about a factor of 30 compared to the previous basically measurements. And neutrinos are typically indicators of hadronic interaction, essentially. So neutrinos are generated in this scenario. So people are interested in possible sources. The location is about Orion, basically the molecular cloud. It's typically well tracked essentially with neutrino, but nonetheless there is no compelling information to source. There's only one event, so stay on hold. Essentially, if you're interested in details, you can look at the seminar at CERN by Pascal or Frank. Actually, and you can see the details there. So let me tell you a little bit about the future of neutrinos prediction. Can neutrinos, today I highlighted again and again about the problem of technology. And one of the big questions for my field, if I may, essentially is, could neutrino physics ever go to surface? Exactly a little bit in the way that happened to us from the anthropological basic point of view. We started basically a lot of our history essentially being in the caves. We actually hide in the caves, and this was for many, many reasons. If you like, survival most of all, and survival of our detectors basically is what pushed us to put our detector down there, to put them underground. And it turned out that basically technologically, actually the fact that basically that humankind basically moved to the surface and later on even to the sky, basically was a technological achievement, tools and things like that that basically got us there. And my basically question is, could we do the same ever with neutrino science? And if we did, that would be a breakthrough. And because the main thing is that this problem with excavation, this was my experiment, actually we're excavating this tunnel close up. Obviously speaking, 300 meters from two nuclear basically reactors, and I was just in the middle of Fukushima. How cool we became when they realized we were putting dynamite basically 300 meters from the nuclear reactor basically in the middle of the Fukushima crisis. And I can tell you that was not very easy. And the big question is, can we get away from without this? It's a pain. Of course, it's a pain that we need to go through because we don't know how to do it otherwise. But the big question is, can we get away from that? If we did, we have to change something. And the main reason this is how our detectors look like, they are beautifully transparent. But what is the problem of transparency? The problem of transparency is that if you have one event here, one event here, one event here, happening at the same time, you just don't know what it puts you. Unless the detector is having granularity and the ability to separate and discriminate things. And that is, as a matter of fact, the main reason this beauty is the main reason we do the detectors underground. So in fact, we need to shield them using even the planet, as a matter of fact, to be able to basically get away from basically these detectors being transparent, long story short. And if we didn't realize this is just basically artificial intelligence, basically, we can make detectors on surface. And if we're able to do that, we can make them bigger. There's absolutely no problem. Right now, our complication to make detectors bigger is only because we need to make homes, and so time. That was just billions of euros actually to make it in homes underground. And then we happen to have the right hole at the right place in the lucky big area. So what we need to do is to basically build new technology that is going to have to be fast, because anything that happens at the same time is going to be able to handle high electricity. Many things keeping the detector at once. It needs to have high precision and high granularity capability. And cheap, because we need to make big detectors. And this is about killing the cosmogenics. And if we were able to remove these basically stuff, is the activation, like basically of the detector, we would get away basically with that. So in fact, you can look at the underground laboratories in the planet. Nobody's able to do any science with less than a kilometer underground. All these are underground laboratories, huge facilities, essentially that have been built because we cannot do that. And the big question is, can we do science basically there? And in fact, I mean, I'm very happy to tell you that with my team, actually, we're building a new technology called Colloquium that I'm not going to really put together to tell you the full detail. But if you have questions, I have a couple of slides. But I want to try to basically give you basically a feeling for what we could do, particularly regarding solar neutrinos, and this is what I do for the end. And here we need to change the paradigm. Detectors are no longer going to be transparent. They need to be opaque. And that is the challenge, how to do that. But I will explain that if you have questions later on. So what we are actually exploring is the possibility of building a large detector close to our nuclear reactor. We are actually funded already with several million euros essentially to build the first prototype and demonstrator there close to a nuclear reactor. Again, a nuclear reactor is basically a neutrino generator, anti-neutrino, which is an antimatter as matter generator. And we are basically exploring the possibility of making a large detector, much smaller than all the detectors that I showed you, so it's actually much simpler in principle. In this position, you may be wondering why there? Why to be there? And this, of course, has almost no requirements. Very basically, a little bit of a onion soup, if you like, about that. And the main reason for that is that we have, I actually work with EDF, a nuclear reactor company, and they have a huge facility of the size of the supernovae detector that you saw at the very beginnings, and they want to get rid of that. That was a nuclear reactor that was running from the 50s and 60s, and they are actually emptying it out. They are dismantling that. And they're asking us, do you want to do something? And we, of course, said this is basically worth about €1 billion if you have to build it from scratch. And we're saying, yes, except that our technology is totally useless unless we have this nuclear technology, and this is exactly what we're doing. Let me tell you, just like a dicer, what we can do with that. We can basically explore the PP chains and the CNO chains if we were looking at solar neutrinos. This was barely seen a few years ago, the CNO for the first time in neutrinos. And the idea would be that we're able to see all the neutrino components. These are basically all the components of the PP and the CNO chain. We can measure every single component independently. These are basically low energy, almost KeV, basically MEV, basically range. And we would have usually almost no background. So we would be able to see essentially the PP, PP, so these are basically the main neutrinos, but also very important, and these are the CNO components, essentially the nitrogen, oxygen, fluoride. If we're able to do that, let me tell you something. This is basically the uncertainties of the solar standard model today. When it comes to the PP chain, people understand things better than 1% level, which is remarkable. Not using neutrinos, not using neutrinos. And this is the CNO uncertainties, and some of the uncertainties is driven by the so-called metallicity, and here we're assuming a certain metallicity. Neutrino precision is these error bars. Long story short, when it comes to neutrinos, our uncertainties are so big, so large, that all the bars of today, despite beauty, It's just very corroborated that fusion is happening in sand. But we're not buying, we're not helping, we are not providing really an insight to neutrinos, despite the fact those neutrinos come from deep inside of the skull, not of the sun. If we did super show, we would go from these arrow bars to this per meal position, and we would go below. That would be the first time with a neutrino detector we would be providing for the first time we would meet on the grill to help out our understanding of the sun. For the first time, we would be really entering into an astrophysical basically range, and that would be, of course, validating precision. The idea would be, of course, not only to validate the nuclear fusion, but we would also validate, use the neutrinos, because we would see the heavier the elements, the deeper into the sun, and we would get instantaneous information as opposed to the light, essentially, of what is happening inside the sun. And of course, that's complementary to all our observations. So, my last slide, what is it to remember from what I told you? But I hope basically I managed to convince you that I went through fastly and briefly. I mean, the neutrinos are everywhere. They are shaping the universe as we speak. Complementary information for everything that we're doing in the IAC, and catalyze the evolution of our ecosystem. So that's the project by Project. What do we do? I mean, how do we link to this to the IAC? In fact, I was wondering, I mean, we're preparing this 300 days that everything you guys are doing is into what we're doing, and that's a beautiful story of complementarity, and that's how science actually works. Yeah. Thank you.
Thank you, Anatael, for the very nice talk on Colloquium. Do we have questions or comments?
Thanks very much, Anatael. Just to point out, the Greek one is missing from there. I have 3 questions, if I may. I'm going backwards from in order of importance. So you must have hinted at it, but I'm not quite sure I understood. What defines the capability to pinpoint a neutrino, like in optical astronomy is the wavelength and the diameter of your telescope? What is the decisive factors in the detection of neutrinos?
This event actually was a new neutrino, so it's a charge power interaction. So the neutrino mu has produced a mu, and what you're seeing is a mu that has a beautiful track and that has directionality backwards, and that tells you a lot of directionality.
But the error on the position, what is that defines it? The uncertainty, the actual uncertainty of the location.
But I probably maybe I'm not sure if I understood. I mean, with the new track, you have an angular basically resolution, and you can point backwards, and that information that providing that.
Yes, but the uncertainty. What drives the uncertainty?
Oh, typically, the scattering on these news probably is a very heavy, very high energy news. Typically, it's the scattering of the news. So there is some random scattering and avoidable, I think, of news. But news go very straight. There is another issue. And the interaction. So the news comes from an interaction, and some of the energy went to the nuclear system. So you get when a neutrino interacts, is passing some energy to the nuclear that is interacting with, for example, carbon or nitrogen or whatever. And then you get the mu, and depending on the type of interaction, there is because of conservation of nuclear or energy flow. I mean, you actually the mu may be somewhat scattered in the interaction point, and there will be some scattering the mu. If you have a mu. And in fact, we are the best for pinpointing, backward pointing, with the limitation of the interaction that we have with maps. And that actually is not straightforward. You need to understand your key maps, very essentially understand what happened in the nuclear system.
Okay, thanks very much. The second one was you showed a plot with basically the number of occurrences versus the energy. And then, yes. Yeah. So what are the error bars on this? So how do we know, for example, that AJ neutrinos even exist? How do you differentiate them? Why is it not the tail of the atmospheric neutrinos?
The first question is actually neutrinos in this range. The first question is that consistent to atmospheric neutrinos? And in fact, if you look at the plot that I showed, typically what you want to see is that this follows the power law of the atmospheric neutrinos, and this is deviating essentially for that. So, I mean, but that's not an open debate. That's the key question. are you really seeing something bizarre in the neutrinos, or are you really seeing something really astrophysical? And that's typically the more you are in that region, in fact, you don't. This is why you cannot do probably anything in that region, because the atmospheric neutrinos are just getting more long story short. This is why people start looking something sexy when you go reading that level.
Yeah, but even there, how many sigma away are you from?
That's that.
Okay, and the third one, what is CP? CP violation, you mentioned it once.
As you know, I would like to talk about these symmetries. So CP is charge parity violation. Okay, sorry. There. So that's these generally most interactions is conserved, and we know that in the weak interaction, CP violation, CP is violated by a little amount of works, and we are seeing basically potential evidence of CP violation in the weak neutrinos. And as you know, weak interaction is P parity violated. So weak interaction has these very funky features about basically the way the angular distribution, and this is why it's to do with the neutrino about the handedness of the neutrino. So it's very, very impactful, and with weak interaction, and what do we go on neutrinos? This is why this ambiguity of neutrinos and neutrinos.
And Anatael, in connection to this, what is the connection of this CP violation with our existence that you have emphasized so many times? But maybe not everyone is familiar with this.
So when the Big Bang happened, probably you know me better than me, we think that matter and antimatter were generated essentially in the same amount. And then there was a lot of this matter and antimatter related in equilibrium and then annihilated, and this became radiation. No, sorry. And of course, we're not made out of radiation. So we're interested essentially in that imperfection with little excess, essentially, of matter or antimatter that we're made of, long story short. And the only way to actually generate, this little excess of matter that is not going to annihilate in this equilibrium matter is going to basically be driven by this condition of CP violation. Normal condition, you have to have a thermal equilibrium, whatever, knows much more than me about detail, but CP violation is one of those necessary conditions. So, long story short, beyond the funky name, this means that particles and antiparticles behave differently. There is an imperfection in their symmetry, and this imperfection is actually what caused basically our existence. This is why if you use quarks, people, this was a baryogenesis. If we believe that we were made out of quark, we actually get multiple mass in proton neutrons. But it turns out that the CP violation in the quark sector, as we know today, is far too small. So we believe right now, well, either there is new science somewhere else, physics somewhere else, or quarks do not seem to be a straight path to our existence. And because we have only quarks and leptons, we're looking at the other possibility that is leptons actually generating essentially our excess matter, and this is called leptogenesis. And this one of the requirements is this feature of the neutrino of being particles and component part. Okay, and it's generating this CP violation at the epoch of the Big Bang and creating essentially this excess matter or antimatter. So you prefer to be essentially have a very long solution, but not a complete.
No. Okay. Thank you, Anatael. Do we have any more questions? If not, let's thank him again for your beautiful talk. And enjoy your lunch.